Okay, cool. So we're going to talk about section 19 today, which is, I think it's listed as statistical distributions under learn. Um, so this is kind of like, if you kind of think of like the past few lessons, I think you and me talked about this a little bit, Eric, but like uh, the past like four sections have been much more like on the programming focus. So like all that kind of like, APIs, HTML scraping. We're kind of diving back into statistics and the mathematics itself. So we kind of like start basically by the curriculum goes through kind of statistical distributions, some of the stuff you've seen, and then we're kind of expanding out further from section one. When we first did it, I think back in like section 9, I think is when we did statistical distributions. So it's kind of interesting to kind of pull back that information, but we'll kind of go over it, and I'll give some brief kind of summaries on some of the things that are going on here. Um, and then that will lead us into basically samples of distributions and t-distributions, which are kind of similar to like z-score, z-test, but more around a sample. So this will all kind of tie it together. Generally, I feel like this section tends to be a little shorter, just maybe the way I do it. Of course, curriculum has a lot more information than I do, but I don't feel like me going into it might not serve it justice. So that's why I don't like go through everything, but we'll see how it goes. Right,
Okay.
so yeah, let me go to start sharing my screen now. And, oh, Zoom cut it off. There you are. Okay, cool. Oh, good. Oh, this is new. Zoom never does this for me. Makes a little window in the side. I don't know what changed this time. Okay, so you should see my screen now. Statistical distributions. Cool. All right. So we could talk about statistical distributions, what, 10 sections ago. But essentially, you can think of it like it summarizes, the probability of events of a system or a group. Usually we talk about the population, but it could also be, in a sense, like a sample. So like a subset of the population. Okay. So we have a few of them here, and you can see I listed a whole bunch of them. And this is like the ones that I think the curriculum specifically states out. We should know uniform distribution, normal distribution, but I'll kind of review that a little bit. So a uniform distribution is like probably like the simplest one we can kind of think of. Uniform basically means that everything has equal probability. So like if you take a die and you roll a die, each side should hopefully have an equal probability of coming up. So and uniform distribution tends to look basically something along like if I drew this out in a graph where we have our frequency, basically it's like, oh, let's say for die, it's like, okay, here's a 1, 2, 3, and so on. You would basically have the number of times the probability it would happen relatively equal. Now, in reality, it won't be perfectly equal. Like if we were to do this over and over and over again, those bars would get closer and closer and closer to being basically equal probability. So if I roll it like 1,000,000 times, we would expect 1 out of 6 times it'll land on a 1. But in real world, of course, if we were to do this in real world, if I only roll it 10 times, there's a pretty good chance that I will only roll 1, like maybe like twice. But it could be less or more or 4 or 5. Or there's even a chance for it to roll all ones, even though it's fair. So just know that as we kind of talk about distributions, a lot of times talk about like with samples is that we have to do it over and over again in order for us to approach what we'd expect our value to be. Okay.
Mm-hmm.
All right. And these are just the equations that came out from the, looking at this right now, this doesn't quite seem right. I'm not sure. But this is like past Victor, like writing things down. I was like, what did you write? But you can expect this, like I think this has come from the curriculum. So just know you can get the mean and the standard deviation. Basically, I think this is what I was writing for, just 2 possibilities, just yes or no, like a coin flip.
Mm-hmm.
But obviously, if you had multiple, values, you would have not just A and B, but A, B, C, D, whatever that represented, or a sum.
Okay. Okay.
So this is pretty simple, like what the average would be versus a standard deviation. The standard deviation should be basically, there's no real spread.
Right.
So that's the simplest one. So we're going to go right off to that one and go straight into normal distribution, which of course is like the most fun one, or not the most fun, but basically a really powerful thing we can use. So here is kind of like a little, I think it's called a Gatton board. And so a normal distribution, this kind of leads into what we'll talk about, the central limit theorem, but basically is that a normal distribution, or also called a bell curve, right, comes up from the fact that you have these things that basically tends to be a very strong like preference towards the mean. and then it gets less and less as we go out. And so we'll talk about this a little bit later, but I wanted to show this board because we'll talk about the central limit theorem. But basically, most things kind of tend to fall into this normal distribution taken over time. And for this kind of ball, I don't know if you've seen this before, but you see those little pegs and it's going up and down. Trying to do this while it's going through real quickly. But like as we drop the ball down, basically it can hit these pegs, go left or right, left and right, left and right. Mm-hmm. So in general, even in the middle, they don't all fall down the middle. Some of them go like, keep going to left because they keep bumping off the peg on the left and keep going across the side. Most of them kind of do left and right about equally. So we end up getting that. Most of them in the middle, and then some of them on the side, off the side, or further and further, further. And basically this comes from the fact that it's a normal distribution. Okay, so that's kind of like a nice visual, and it's a pretty classic one. I think it's called Gatton board. I could be wrong. But this right here gives us our distribution. Basically the probability of it falling within that X part is, and there's a continuous distribution in this case, like meaning that we can have any value of X from like a certain range versus like a very discrete value, meaning like it can only be 1, only 2, and whatnot. So again, we've seen this equation before. You generally don't need to memorize this equation. It's useful in the sense of being able to pull it up basically with our sigma here, which is our standard deviation, and our mu. So basically you can generate normal distributions very quickly by just knowing what the mean is and what the standard deviation is. Or if we want to generate a standard a distribution for some kind of simulation, and we say we want to be normally distributed, we can say, all right, we want this mean and we want this standard deviation, and we can put that in there. And note that usually, I'll put standard deviation for most of these equations, but most times statisticians will say variance over standard deviation, usually because variance is a little bit easier to work with. But I'm telling you guys standard deviation since you guys are probably more familiar with how that is related to the spread of the data.
Okay.
Cool. So hopefully that's kind of review. Okay. No questions on that, I'm guessing. Yeah. Cool. All right. I'll put that away. So binomial distribution, we've kind of seen this before. Binomial distribution, you can kind of think of it, I give it a little phrase here, probability of getting the number of successes in a given number of trials. So you can think of it as like how many, if you flip like a coin, it's like how many heads, or the probability of getting 5 heads when I flip the coin 10 times, what's that probability? Okay, and then we say, oh, what's the probability of getting 4 heads with 10 flips, and so on, right? And that's what our binomial distribution is. And you can kind of see it's basically, it's a discrete distribution versus a continuous. And usually we kind of end up getting like a normal curve right here. As we get more and more, in this case, in this graph from Wikipedia, as we increase K farther and farther, like basically the bigger the range of K, the more different possibilities we have, and it'll approach a normal curve or a bell curve. Okay. So you'll see some useful equations. These just come from, again, from the curriculum, where P is basically the probability of basically success. So they're talking about like for a binary choice. So either a yes or no, a heads or tails kind of deal. Note that you don't have, like for a coin flip, it's 50-50, but P doesn't have to be 50-50. P could actually be like, maybe this coin happens to land on heads 70% of the time and only 30% of the time on tails. Okay. And so this right here, this is what the combination, I think, if I remember this right. Basically, this is usually represented by, I can't remember what it looks like, but or how to describe it. But usually when we write this part, you'll usually not see it written out like this. You'll instead see it written out in this notation, which I think you guys have seen before. And this would directly translate into here. And it's just shorthand notation, essentially, to say, all right, this is how to do the number of combinations. Yes, combinations. So number of combinations, and then basically saying the probability of getting that success in these trials. So binomial or not binomial. Well, it is binomial, but binomial distributions are another really common one. So I think between normal distributions, bell curves, and binomial distributions, because they're related, you'll see these like the most common. Okay. And then that kind of ends like with all the stuff that we've learned before. And so this gets into a few distributions that I don't think we've talked about at all yet. So the first one is a negative binomial distribution, which in my opinion is a mouthful. It can be kind of tough to say all that, but a binomial negative binomial distribution, okay? It's a little different from the binomial. So remember the binomial was the probability of getting so many successes in a given number of trials, okay? So the negative binomial distribution, it's the probability of getting a number of successes within a given number of events. So one example of this, and I think the curriculum kind of shows this, is that we keep flipping the coin until, what's it called? Until we, we stop flipping at 2 tails. So like if we were to keep flipping, if this makes sense. So I'm going to try to do a little game here. Is like if we say, all right, you're going to flip the coin until you're until you hit 2 tails, or not 2 tails in a row, but there's 2 tails, we'll stop the game. How many flips would you expect? So for example, what's the probability of doing 9 flips if I flip the coin, flip the coin, flip the coin, flip the coin, and once I get 2 tails, I stop flipping. So this is what the negative binomial distribution is. You can see it's kind of similar to that binomial, right? Probability of getting the number of successes in a given number of trials. This one, we're fixing the number of trials and saying we are only doing 10 flips or 9 flips of the coin. But the negative binomial distribution, we say we keep going until we hit that, our fail metric essentially. So our fail metric in this case is, when we hit 2 tails. So like, or you can think of like 3 strikes you're out, or 2 strikes you're out. So we're just trying to figure out like, well, how far can we go? How likely can we go? So well, technically we could keep flipping and get heads and over and over and over and over and over again, and we'd go on like for 100 years flipping our coin. But the probability of that happening is relatively small. So this is right here. It's from Wikipedia. It was kind of a nice kind of thing. This R right here represents the rate, basically how many times you'd have to get a failure until you stop. So if you only have to fail like 4 times, you can see basically you have a pretty good chance of getting a pretty decent number of flips, going through. But as we increase, this R right here, as we say, we have 40 failures, okay, we can actually see how far we can go further and further and further out. Okay, so negative binomial distribution, again, related to the binomial, but you can see there's a slight difference. And we'll see something similar with the Poisson distribution. Okay, so what's kind of nice is that the mean right here is basically just this R, basic meaning, and this R is just a number being that how many failures do you need, okay? And then standard deviation is kind of similar with how we derive the binomial distribution up on top here. So you can kind of see like the similarities within here. Okay, cool. All right, any questions on negative binomial distribution?
Nope.
Okay. All right, and I see Adam, you came in too. You have any questions about this? Hopefully you're all right. Cool. All right, so geometric distribution, you can think of this as like a special case of the negative binomial distribution, but basically the geometric distribution is when you have just one failure. Basically you keep going until you have one specific failure. Okay, so in this case, I think in the curriculum it talked about it being K. I could be wrong, but it just all depends exactly what it is. Basically, geometric distribution is just a special case, but because it's used like where we have one specific failure and it stops, okay, it's kind of like, I'm trying to think of a good example of this, but like, it's like, oh, you keep doing things until you're dead. It's like, well, you only fail once. Once you fail once, it's kind of like, okay, we stop right there. That's why this is really common. But just know it's a special case of the negative binomial distribution.
All right.
Cool. So kind of going through these distributions pretty quickly, because again, there's a lot of information in the curriculum. So if you feel like there's more to be had, definitely can go back to that. But for Poisson distribution, okay, so I'm going to read this kind of definition off here. It's the probability of having the number of occurrences or successes in a given interval. And usually it's measured with an interval, meaning time or space. Usually time, usually Poisson usually falls within this amount of time. So I think one example the curriculum talks about is, let's see here, is if like on out, like, on average, there are 20 customers that come walking in to a store within an hour. What's the probability of no one coming into the store in the next 20 minutes? So like, there's like, basically you're trying to say how many times does this happen within a given amount of time. So it's kind of like the continuous version of the binomial distribution. Okay, but usually we relate this to time because time just tends to be, we say that's continuous. So usually you can factor in time as small as possible. So usually when you're talking about time, you'll usually end up Poisson distribution. Note that basically any binomial distribution can turn into the Poisson distribution if given enough splits, if that makes sense. And so we can actually, or say binomial, it really should be negative, shouldn't it? But anyway, you can kind of think of like how many times this happens. And so these are different shapes, for example, is that this lambda equals 1, lambda equals 4, and lambda equals 10. That's representing of how often those things occur, kind of deal. And so you can kind of see as we get closer and closer to a larger lambda, we actually get closer to what looks like a normal curve. So you'll tend to see that, but you'll still see, like if you look carefully, you actually see like this lambda equals 10 actually kind of slant out to the side. Okay. And again, this is really useful, or really common when we're talking about time, or distributions within time. So like, I think another example the curriculum gives is something along the lines of a police officer gives about 3 tickets on shift during his shift. What's the probability of him only giving 2 tickets within his shift? Okay. And so these are the kind of like, that's the kind of problems that you would kind of come across and what kind of distributions you have. One thing I should note though, is that it still assumes that these events that happen are independent. Yeah. So for example, a cop giving 2 tickets, him giving another ticket has to have the same probability of happening. It shouldn't be like, oh, now that he gave 2 tickets, he's more likely to give a 3rd ticket. That won't fall into a Poisson distribution. So Poisson distribution, or Poisson, relies on that each event is independent from each other. Okay.
Yeah.
All right. And what's kind of fun, this is the distribution right here. So the probability, how you'd find this. Lambda is just specific to the problem of saying basically the number of events that you would normally have in the same interval. What's kind of cool though, is that basically the mean, I think I have this wrong right now. I have to double check. I think this should actually be just lambda, because we're talking about the standard deviation. But what's kind of cool about the Poisson distribution is that the mean and the standard deviation are exactly the same, and it's just simply lambda. So it's kind of a cool little thing that comes out. I believe that's correct, because I believe the variance is actually lambda squared. Maybe I'm wrong. Double check on the curriculum, because I feel like I might have messed something up here, and I'd have to check. Pablo, do you have? You might. Do you have it, Pablo?
Yeah.
Yes, I do.
As far as I recall, the property of Poisson is that the mean and the variance are the same.
Right. Okay, it's the variance. Okay, so it should be square root.
You were correct the first time around, yeah.
Okay, cool. I felt like something seemed wrong in my head, but I think it's because I wrote everything in standard deviation instead of variance. But yeah, so that's a kind of a cool property of like the Poisson distribution, is that those 2 values are in fact the same, and they're just simply pulled out from lambda. So kind of a cool thing. Anyway, this is why, like, for example, kind of going back a little bit, like to section 1, where we talk about like a PDF, like a probability distribution function, being able to get that parameterized. If we have something that has an equation essentially that's associated with a distribution, we love those equations because we can pull out this mean and the standard deviation really easily, really quickly, or we can simulate these very quickly and easily. That's one of the reasons why we like those kind of things. But remember, like our KDE is not one of these kind of equations. KDE basically tries to build up a more organic kind of distribution function. So anyway, something to kind of note on. And this leads us to exponential distribution, which is kind of like the opposite of Poisson. So one way I've heard this described as a continuous version of geometric. So the way you can say this is the probability of an interval of a given length to occur before an event. So you can kind of think of it like, how long will this happen, or how long will it take for this to occur? And one classic example is like particle decay, like uranium. So I don't know if you guys did anything like for, like, this is where like, physics background comes from, because like this is like all we talk about. But like it turns out like for uranium to decay, uranium will randomly, with a half-life, you guys probably heard of half-life. Basically, there's a certain over a certain amount of time, this half-life, half of the uranium atoms would be decayed or would decay to something else. And so you can actually measure that thing. But it turns out for any one particular uranium atom, you don't know exactly when it will decay. Okay, you can measure on average, these many different, uranium atoms at once, how often, how long it takes for it to decay. But it could take, let's say you start observing a uranium atom. It could take like 5 seconds. It could take a million years, and you have no clue when exactly it'll decay. So you can actually find the probability of this, and this is essentially this exponential distribution. It's usually associated with decay in that sense. So a lot of times too, you'll see these equations with like lambda, but a lot of times in certain fields, you'll see also it described as beta, or 1 over lambda is beta. Basically, it's decay factor, or I actually messed up my vocabulary, but basically it's like describing how often it decays. And that's when I say decay, it happens once and then you stop counting, because it basically, once the particle decays, it can't decay. Well, it can decay, that thing can decay again, but you're done counting basically. So you can kind of think of it similar to how we say there's a stopping factor, but again, continuous version of geometric. Okay, cool. And you can see here, similar thing with the Poisson distribution, where we have our standard deviation and our mean being equivalent to each other, which again makes me wonder if this is right. But no, I think this one is correct in this way, but maybe wrong. Okay. Anyway, those are all our different distributions that at least the curriculum talks about. So do you guys have any questions in general of these distributions, anything that we kind of showed? And again, they're nice because they're mathematical objects. And we love when things fall into a mathematical object, because then we can very quickly describe them or identify them and pull out information. Cool. All right. So that'll move us to our sample distribution. So this is a little discussion. About halfway through the Learn curriculum, kind of goes through a bunch of the distributions, statistical distributions, just describing what they are, just kind of like what I did. But there's a lot more information, so I'd definitely go through it all. But halfway through that, we go into basically to talk about sampling distributions. And so for sampling, basically, this is kind of a basic question. You can kind of get an idea. When we do a sample, when we do like you can think of it like a sample being a survey, okay? When we do surveys, why don't we ask everyone? Like, what are some reasons why we wouldn't do this?
Just takes way too long. I mean,
yeah, it takes some time.
You don't know how to reach everybody, and all sorts of different stuff.
Yeah, exactly, right? Like if you're doing a survey and you're trying to reach out everyone, first of all, it's going to take a long time for you to get everyone, okay? It's going to take more effort, right, for sure. It also tends to be more expensive, which kind of goes along with effort. This is actually kind of an interesting part, is that like when we do like the US Census every 10 years, it's kind of like required by law, like it's the way it's written. It's basically, it's like they need to get as accurate as possible, which means like if someone doesn't get a response back, like for example, if you give out your survey form and you don't get responses back, most surveys will just say, all right, no one respond, like they didn't respond, we'll just won't count them in the survey. That of course is going to introduce bias in that sense, because maybe there are reasons why that person didn't respond back, which means that now you have kind of like a different sample. Basically, it doesn't represent the population, which is what you're trying to avoid with sampling. So the census actually requires that they try to, if you like don't answer, they'll come back, they'll come in person, they'll kind of keep going through, which of course can be really, really expensive. I don't know if you guys are following this particular part of the news for the census, the 2020 census, but there is actually kind of an interesting part right now that's kind of being debated about what's being included. Have you guys heard about this at all? One of the things right now is saying whether they should include in the census data if you're essentially like an illegal immigrant or not. And it's not that they're necessarily going to use that information directly and say, if you check that box, they're going to say, gotcha, and then come get you or whatever. But there's a concern is that if by putting that in the information or in the survey, is that people who are illegal immigrants wouldn't want to respond back. And that makes it much more expensive, because basically instead of just ignoring those people, they might go in, or what people might do is they might lie. Like they might say, oh no, I'm not a legal immigrant, but then also biases their data in that sense too. So that can be kind of an issue. And there's kind of a topic of like saying, oh, what should we do kind of deal. So it's kind of real life problems, right? Big surveys. But anyway, reason why we're doing this, typical stuff. We don't want to ask everyone. It's too expensive. It's too hard. It's too much work. But it turns out that's okay, because when we do sampling, we can actually make sure we get good results. We can actually get decent results from our sampling and understand what our sampling, or if our sampling describes the population or not, and without having to ask everyone. And it turns out it's not that many. You don't actually need a huge amount of the population to get a pretty decent idea of understanding the whole population as a whole. Of course, as you get more and more, that can give you more information. But it turns out sampling is actually a pretty good tool that we can use. Okay, so let's see here. So I did go on. So at first I was going to like write out a whole bunch of stuff, but I realized like the Learn curriculum actually does a pretty good job of showing this information. So I kind of want to show you guys a little bit of what this looks like. So let's see. So I think they showed here. So some sampling information. So like, I want to make sure that this is what I was looking for. So I think in this case, they actually did like a random, like they basically did a random sample. They created a random sample. And you can see here, it kind of falls into this like a normal distribution, but you can kind of see that there's kind of like some spikes here. Some they're more more common. There's some less here. So the curriculum actually like tries to make like a random sample, which actually kind of like something you can do, which is what we'll typically try to do like when we're trying to create like something like a simulation or trying to compare a sample or our own sample with what we'd expect it. We might try to generate a distribution ourselves to kind of compare the two. Okay, so just kind of want to show you guys that existed. But definitely go through the curriculum because it kind of goes through a lot more. Now, there's one part in here that's super important. It's called the central limit theorem. And I think we mentioned this before, but very lightly back maybe in section 9, right? And the main thing is that the central limit theorem basically tells you that there's a tendency for, as you sample the data over and over and over, or if you take many samples again and again and again and again, those samples tend to form a normal distribution. Now there's an important caveat to that, is that those points have to be, those samples have to be random and independent. So this is where like surveying, for example, can be an issue where if they're not random, then you won't actually approach a normal distribution of the population. But what's really cool about the central limit theorem too is that if the population is not normally distributed, it's okay, because the distribution of the samples, called the sampling distribution, will actually be normal. And what's kind of cool is like once you have that normal distribution, we can actually do a lot of the mathematics around that. It's really nice to be, like, again, I kind of keep emphasizing is that we like the normal distribution because we know the mathematics. We can actually do a lot of the different testing. We can work with that kind of information. So again, though, I want to emphasize is that it's the samples themselves, the distribution of the samples, that actually will approach this normal distribution. Okay, so you can imagine basically if you do a really good survey, for example, and you do 50, you basically reach out to 50 people randomly, right? And you get that part. Well, those 50 people might not represent the whole, let's say you do it for a state like California, which has a lot of people in it, right? Millions of people. You're probably, with those 50 people, you're probably not going to get a representation of whatever you're trying to sample across, right? Like, you're probably not going to get a good representation. However, you can essentially keep doing these samples of 50 people, 50 people, 50 people, 50 people. And the distribution of those samples themselves will actually fall under a normal distribution, even if the population itself, like whatever you're trying to measure, isn't normally distributed. So it's a really powerful tool. And the curriculum kind of shows it very quickly, but I just wanted to like emphasize like that point, is that it's not the, what's it called? It's the sampling, it's the distribution of the samples, called the sampling distribution. And again, it allows us to do some really cool stuff, because essentially, if we get into that nice form, we can do all the mathematical, we can use that mathematics essentially to do different, tests and extract information from that sampling distribution. Okay, cool. So that's our central limit theorem. And that's an important part that will kind of keep coming up, how we can assume this. So sampling statistics, basically, this is like, this is one of those things where it's like, it feels really basic, but you have to be a little careful, is we already know, like, for example, finding the mean the population mean, the standard deviation, right? The variance of the population. When we want to find those values specifically on a sample, we have to be careful of how we approach that in the sense of like what we're trying to look at. So we'll actually talk about like, for example, you'll see the mu. Mu usually represents the population. You guys know what I'm talking about when I say mu, right? It's that weird looking U looking thing. It's a Greek letter. I realize like you guys might not have actually have heard it said out loud, but it looks kind of like that sometimes. Okay, so there it is. Oh, mu, right? So that's usually talking about as a population mean. Okay, so which is very different from our sample mean, right? Because if we took if we took 50 people out of like, 10 million people, those 50 people might have a very different, average than the actual whole population average. Okay, so usually we talk about it as the sample mean, meaning it's the mean of the sample, right? But we'll make that distinction, and usually, for example, X bar, depending on the field, they might write it differently, but usually X bar is considered like, oh, we know that is the sample mean, not the population mean. Okay, and then we have a little different here for the sampling error and the standard deviation error. So before I guess move on to there, the sample mean is, as you probably would expect, is just the average within that sample. So you add everything up, divide by, however many options you have, all that, the normal stuff you would have. Okay, but it's just within that sample versus the whole population. And note that we usually don't know the population mean. Like, think of it this way. We don't know everything, because how would we have, if we need a sample, like if we try sampling, we probably don't know what the population mean is. There's sometimes we can kind of reason things out of like how we know or what we think the population mean is. But in most practices, we don't actually know what it is. We might have an idea, but we don't know what the truth is. Okay. But sampling error versus the standard deviation are related to each other in that way too. That sampling error is kind of like this quote unquote standard deviation of the sample. But note that we call it specifically the sampling error because it's not the standard deviation of, it's not simply the standard deviation of the sample. It's a little more subtle than that, which I'll kind of get to it in a second. But the main thing is that it's describing the sample. It's not describing necessarily the population itself. Okay, and of course, this all relies on the fact that it helps us understand if we do a good sample, if we're doing a good survey, for example, to make sure that these like sampling error, it allows us to compare our sampling error, our sample mean, and compare it with the population. And we'll actually see whether or not it belongs to that population, or if we basically, did we do a good job surveying, or is there some bias in the way this specific sample relates to the population, which we'll see in T distributions in a second. Okay. I just want to kind of quickly just show you a little bit of this that's going through. Basically, they have like a simulate. I think they just made up these numbers. Basically, they're different pumpkins. Okay, and they kind of walk through basically. Okay, first we can figure out what mu is because we know what all the pumpkins are, and I think this is like how heavy they are. So it's like, okay, we can quickly do that just so we know what the quote unquote truth is. Okay, and so we have that information on there, and then you can basically calculate the mean of the samples. Okay. And so that's pretty simple. You basically grab a sample. In this case, their samples of 2 pumpkins. And so you just take the average of that weight. And what they basically do here is they'll, it's part of the lab, so I'm not going to actually do it for you guys. But you actually will just like calculate the sample, the mean of the samples. And you can actually see, well, obviously that sample mean is not going to be the population mean. But it turns out if you do all the samples like this, you will actually approach, and you can see here's the different sample means for the weights, okay? You'll actually approach the true population mean, okay? This mu part. And so essentially, this is what we're talking about, like the distribution of the samples itself actually approaches a normal distribution in that way, okay? And then I believe here's I was talking about the sampling size sampling error. So think of it this way, is that if we increase, like, we can kind of think of like, if we take, let me ask you guys, and this seems probably pretty obvious. If I take a sample of 50 people versus 5,000 people, which one's probably going to be a better representation of the population? The 50 people or the 5,000 people?
5,000.
5,000, right? You kind of intuitively get that. It's like you get more people, you would expect it to be closer to the population. That's kind of like what the sampling error is really trying to show, is that when you have more people, it's no longer just being like, oh, well, there's a spread of this, information, like the standard deviation shows how much spread. The sampling error also shows spread, but also kind of encodes, well, if you have more people, then you're more likely to have something that's close, like it's more representative of what the true spread is. So for example, if I pulled up like two people, like if I pulled up like, two people randomly out of like 10,000 people, and let's say their weights are like 200 pounds and 100 pounds, okay? Well, it's possible that like maybe that's the true, maybe there are like a huge spread of like number of people, or it could be just be possible that I just picked some really like, not big outliers, but like I might have picked like a really big outlier, which makes it look like the spread of the data is. But if I try like, instead of grabbing two people, I grabbed like 1,000 people, and I find out like there's a high number of people who are like 100 pounds and like 200 pounds, and basically like it's not just one person's 100 pounds, it's like, like let's say out of 1,000 people, I get like something like 100 people that are 100 pounds, then I know the spread is like, oh no, the spread is actually pretty wide. Versus if I get one person who's 100 pounds and then most people are around like, let's say 180, then I know the spread's not as big. I just happened at that very first person, I got someone who's on the far end of the spectrum just by chance. And that's kind of like where we can say, well, if we get more and more people, we can actually understand what our, we can say our spread is, our standard deviation, our variance, is closer to the actual population's standard deviation. So what we do here, I think it shows here it is our sampling error is basically divided by the square root of n. Now, I believe, and probably you can chime in on this chart because I always mess this up. I believe in certain situations, we actually are supposed to add by 1. And I can't remember what specific situation we do that in, instead of, so we do like sigma divided by the square root of n plus 1. And I can't remember the specific reason what it is. I know mathematically it is, but it always comes up and I can never recall. I don't know if you can chime in on that, Pablo, or if I even have that right. No, all right. Right. Just be aware that there's certain times that happens, and I can't remember the specific point, but you'll come across it, I swear. And I feel like I should be a better statistician for that reason, or like I should be like more knowledgeable in that, but I'm not. So those are my knowledge gaps. Just be aware. But just know in general, as we get more and more of the population, or more and more in our sample, we can say, okay, our sample approaches the standard deviation. Okay. Cool. All right. So I'll move on to the last part, which is our confidence interval, which is really fun. So our confidence interval, I believe we talked about already, right, in section 9. Does that sound familiar, right? So we'll usually say something like, oh, a 95% confidence interval, right? And what we really mean by this, when we say like, oh, the confidence interval is 95%, what we really mean is like, if we repeat this process, basically if we, I'm going to take a step back, talk a little fast today, is if I have a sample, right? So I take this sample and I have 50 people or whatever it is, right? I can say that, okay, there's a confidence, and I have a confidence interval of 95% from this point to this point. So like from like 20 to 80, okay? And basically I'll say like, oh, my confidence interval of 95% goes from 20 to 80. What that means, and sometimes people misinterpret it, but what that really means is that if I were to redo my sample and do it again and again from the population, so I keep taking out from the population a sample, another sample, another sample, another sample, another sample, another sample, is that 95, if I were to make a confidence interval for each one of those samples, okay, 95 of those 100 samples, sorry, 95 of those intervals that I make for those 100 samples, 95 of them will actually contain the population mean, okay? So basically we can expect that like whatever X% of the intervals would actually contain the true population mean. Sometimes you hear people say that there will be like, those interpret the confidence interval is that there's a 95% chance that the population mean lies between 21 and like 80, but that's not what it means. Like the reason why is partly because the population mean doesn't change. The population mean is like a static thing. It shouldn't be something like, oh, there's a probability of it falling in there. These like little slight semantics, but the idea here is that instead it's like if you did the sample, your specific sample, you're 95% confident that the mean should be within this interval, because if I were to do this over and over again, 95% of the intervals would actually contain the true population mean. Okay, does that make sense? It's a little subtle thing, but just wanted to put that in there. Just know that people sometimes misquote it, and it's kind of like the null hypothesis I have mentioned way before, is that sometimes people just misquote how you accept or reject, like a null hypothesis. But that's really common. Cool. All right, so that is kind of sampling distribution statistics. I know I went through this really quickly. There's a lot more information. It's a lot of reading, to be quite honest, in the curriculum. But I think that's because there's a lot of like subtleties and a lot of like nuance to these subjects. Pablo, did you want to chime in with something?
Yeah, sorry. You were talking about the standard deviation of the sample a bit ago. And I just wanted to talk about what you were talking about when saying n-1. Right. So I was thinking about it. It's actually called something like Bessel's correction. And what happens is that if you remember how you calculated your variance and your mean, your variance is calculated around the population mean, right? You're trying to measure that distance from some observation to the population mean. In sampling cases, we don't tend to have that population mean, right? We have just some proxy, which is the sample mean, which ends up making this distance that we have between like your observation and the sample mean kind of biased with respect to the population mean. So this n-1, instead of dividing by n, just kind of makes the dispersion a little bit bigger. So it corrects for the fact that you're going to get shorter distances for that variance when you're using the sample mean. So that's it. Yeah.
No, thank you. Yeah, I know it was something like I could not reproduce that for sure. Like I just remembered it was something, and I was thinking like degrees of freedom. Like no, that doesn't seem quite right. It seems related to that way. I definitely, maybe I'll share with you guys something after this class. Maybe I'll share with you guys so you can kind of read it through, because it's something, a subtle thing that I think the curriculum, depending on what I want to say, it pops up somewhere that we see in the curriculum. But just be aware that sometimes you'll see this part, and it's exactly what Pablo was kind of describing, right? It's basically the way you're measuring how, you're basically measuring along your sample. But I'll skip that for now because that's not super important in this moment. But just know in general is that like as we increase our numbers in our sample, our sampling error will get smaller and smaller, which makes sense. Like, oh, you're more confident with how spread out your data actually is. Okay, cool. All right, so that leads us into our last pit, t-distributions. So our t-distribution is kind of similar. Like I like to think of it like similar to our z-score and our I think z-distribution, stuff like, not z-distribution, but like our z-score and our z-statistic. One kind of interesting kind of thing from history is it's called, usually sometimes it's referenced as students t-distribution because that's how it was first published. It was actually published by William Gossett. I don't know how to pronounce his name exactly. But it was actually discovered by him, or developed by him, I should say. But he was working for Guinness Breweries, the same Guinness, the beer company. But the beer company essentially, Guinness basically said, you can't publish with your name about stuff that you're doing. So basically, he was trying to figure out how to make better beer, which is kind of cool. But basically, they said, like, you can't publish under your name about something while you're working under us. And so he basically put it under a pseudonym of students. So sometimes you'll see it students t-distribution, but really it's developed by William Gossett. It's kind of an interesting kind of thing that kind of comes through history. But the t-distribution really comes from the fact that we don't know the true population distribution. We don't really know what it looks like based on our samples, right? The idea is like you have a sample, but you actually don't know what the population looks like. So you can use basically a t-distribution over something like a z-score, and the z-statistic allows us to basically factor in, it's like, well, we might have more of a spread of the data from our sample itself. So you can kind of see similar, this is directly from the curriculum itself, but you can see it's similar to a normal curve, but you can see that it kind of drops off here. Like it doesn't quite drop off as quickly. So this red is the t-distribution with 1 degree of freedom, which we'll talk about in a second. But basically the normal curve right here is much spikier. We have less likely to land in these edges. And that kind of makes sense if you think about like what I just was talking about before. If we have sample standard deviation, we don't actually know what the real spread is of the data, right? We might have by chance just gotten something off the side. So we're kind of accounting for the fact that we really don't know what the spread is. But as we get a better, more and more, like, what's it called? Like more and more samples, like more and more data points in our sample, we can be more and more confident that we know what the spread actually should be represented by. Okay, so you can see here, and this is from the curriculum, is that degrees of freedom, essentially, the more data you have, basically the less ways it can kind of vary through. The more data you have, the more confident you can be kind of like, oh, like I know what the spread is. And so that's actually why you see the t-distribution actually get closer and closer to a normal curve. And of course, as we get, an infinite number of degrees of freedom, we approach basically the normal curve. But what's kind of interesting is that you can see here with 1 degree of freedom, it's roughly normal, but you can tell like, oh yeah, you got these big tails over here, right? That kind of extend outward. But as we increase more and more, it very quickly, within like, within 5 standard deviations, it's pretty close. And then as we get into, not standard deviations, 5 degrees of freedom. And then as we get to like 30 degrees of freedom, okay, you can see it's pretty much in that red. The green are the old ones. You can see that green, the red, it's pretty close to that blue normal curve. And so this actually comes from the, not comes from the fact, but this is one of the reasons why you'll hear it say that basically if your population, or not your population, your sample size is greater than 30, you probably can use a lot of the statistical methods here because it roughly, our t-distribution roughly represents a normal curve using the degrees of freedom we have. So that's kind of, you'll see that kind of coded, and that's where it's coming from really, is that the reason why is because basically with this many degrees of freedom, we're pretty close to a normal curve itself. Okay, so that is our t-distribution. And the reason why we actually do a t-distribution is essentially just like a z-score in our z-statistic, is that we're basically trying to figure out, does our sample follow the population, or does this sample and this sample, are these related to each other, or are they actually something different? So if you imagine, if you pull by chance a sample that's way off, in the tails over here, there's a chance that you just randomly happened across the sample, but there's a high chance that maybe that you just pulled a specific kind of sample. So for example, I think, okay, imagine like you kind of like grab a bunch of random people off like, I don't know, off a bus, right? And let's say the population mean should fall in about like, let's say a 200-pound average for the average of people, right? The 200-pound average. And you get all this like people off a bus, and you find that their average and their spread basically ends up being closer to like 250 pounds. And you're like, like, is this because I just happened across a bus that happens to have heavier than average people? Or is this bus representative of something different from the normal population average? There's some bias in the sense of me grabbing this specific bus, this specific sample. That's kind of the stuff that you can do with a t-distribution. Essentially say, hey, like, how likely is it that these guys should be part of the population? Or is it that I just happen across a bus that is just maybe geared towards more heavier people for whatever reason? Okay. That's kind of like the idea of what we're doing a t-distribution. And again, it's similar to our z-score, so I won't go into full detail or z-statistics, right? But kind of just showing you a quick example of what this would look like. So this is doing our confidence interval and their t-distribution together. So I'm just going to go ahead and run this part. And I'm going to basically create this. What's kind of nice is that stats right here, SciPy stats, actually I can create a t-interval. And so if you remember doing like stats like in high school, you might have like a big old like chart with all the different values that come through. Basically, it's because the reason why that chart existed is because you didn't have to do all the complicated math. But now we have computers. The computers can do all this complicated math for us, so we don't have to use a chart, right? But basically, we're taking this guy right here. We're saying, all right, we're going to do a t. We're just going to use a t distribution. Specifically, we're going to make an interval. Our alpha is equal to this confidence interval. So basically, this alpha is basically our kind of like our critical value of saying, like, what do we want it to represent? In this case, I'll say, oh, I want it to represent with a 90%. I want a 90% confidence interval. Okay, degrees of freedom, that basically tends to be, I mean, it's not always true, but it tends to be however many people are in our sample minus 1, okay? Because basically the number of ways you can vary the data. So that's why it's like this degrees of freedom, okay? And then log here, just know that's the sample mean itself. So that's like what we want this interval to be represented around 65, and a scale of 18, which is just the standard deviation from the estimate, right? So we have this interval that goes from here to here, and you can see here with a 90% confidence interval, we have this case 35 to about 94.8, right? So you can see here is that that's actually a pretty wide margin if you think about, like, we say the average is going to be like 65. And if I actually decrease this confidence interval to like 10, you can actually see that the interval start to the beginning gets much smaller. It's 62 to 67. And the reason why we can say this stuff is that the reason why we're less confident with a smaller interval is that there's a chance that we missed it. So to increase our, as we increase our interval larger and larger, we just know that we're more likely to actually capture the population mean. So you can see, for example, if I do like 90 again, let's see if I can just go ahead and put this in here. Okay. So if we do like 90 here, we could do that. But if I do like 99.9, you'll see this confidence interval get a lot larger. You can see negative 47 to 177. So I can be a lot more confident by basically increasing my interval. But of course, that might not make a whole, like, might not really help you out, because it's kind of like saying all the possible ranges of people. If I wanted to be 100% confident, I could just say, well, what's the lightest someone could possibly be, and what's the heaviest someone could possibly be? It's like, well, then the population mean must be within that interval. It's like, well, that doesn't really help. So this is where like that confidence interval is kind of a balance of saying, well, how confident do we want? What kind of confidence do we want? And then also, what kind of range are we actually going to look for? So just kind of know intuitively that that's why the interval is getting bigger or smaller. Okay. So here is a sample of some data. So I'm going to generate a sample basically, or samples with 54 mean, 17 standard deviation. And it looks like 100,000 points. So I have this part right here. And just to kind of look at what this looks like, you can see there's 100,000 people. You can see the mean is about 53.9, which seems pretty close to 54, right? So as we get more and more people, it gets closer and closer to actually be there. But if you look at this distribution, okay, you can see it's a little spiky. So that some people are very low over here. And this is just a random distribution. It doesn't really matter what these numbers represent. But you can see that there's very few people who are very far away from the mean, which again was about 54. But most people tend to fall within this area right here, okay? And again, you can kind of see, like, you know, our standard deviation 16.9. That's pretty close to here, okay? And then we can actually get our t interval, and this would allow us to actually do our t interval, our confidence interval for a t distribution. And you can see here, if I run this, it's like, okay, we have a 95% confidence that our population mean would fall between 20 and 87.2. So you can kind of see like 20 to 87.2. There's a pretty good chance that somewhere in there is our actual population mean. Note, however, if I decrease the size of this, so for example, if I go to like 500 samples, same exact thing, you'll see though that our mean can be kind of off. Our standard deviation's pretty close still, okay? But you can see it's a lot spikier. We might have some spikes here. We can't really tell as easily, so our confidence interval will actually change over. You can see it's expanded out. And if I go in the real extreme part, if I go closer to like, let's say 50 people, you can see, in this case, our mean is pretty close. Our standard deviation, you can actually tell, is actually not as close as it was before. But that's because we have more spread, basically. There's a less certainty of like how our spread is. And so we can see with our confidence interval, we actually have these parts where it's like, well, we can still confidently say with 95% confidence that we capture the mean. So you can kind of see, like, even with a smaller smaller sample size, we can actually get a pretty decent confidence interval. Okay. So yeah. And you guys have any questions then? This kind of finishes up anything I wanted to go over.
I'm good.
Okay, cool.
I mean, it's a lot to digest, but you know.
There is a lot, yeah. And I feel like, sorry, go ahead. Yeah.
No, go ahead. I'm just.
Yeah, I definitely would suggest it. What's nice is that the curriculum, I mean, debating nice, is that there's a lot more of reading in this curriculum. And I would suggest don't just simply go through it really quickly. Like really understand, like, what was it trying to tell me? Because the math itself isn't necessarily difficult. I mean, most of the code is really easy for you to write, but understanding like how to use these functions, how to use, what's it called? Like use these distributions, like actually perform these things. Like when would you use this? Like, you know, how would you do this test? That's the important part. And that's only really done from like the context of understanding when are these tests going through? How do you get the standard error? Why does the standard error get smaller, you know, as we increase like the sample size, like those kind of things. But the math itself is not necessarily difficult, right? Like I could give you this in high school and you probably could figure out, you know, if I gave you the numbers, you can plug it in pretty quickly. But that's not the part that's really difficult. It's mostly this stuff here, why it's important. Okay. Awesome. And Pablo, do you have anything that you wanted to add in? I don't know if I...
No, actually, this was really good. One more mention. I guess one thing that you did say, but like I think it's important to talk about. One of the reasons why we like t-distributions for samples is if you note, the tails are pretty fat at low sample sizes. That just means that they account more for the fact that you're using small sample sizes and you might see very unlikely events in those samples than you would if you had like, you know, bigger ones. So that's one of the big reasons why we like it.
Yeah.
You did mention that, but I thought it was important to mention again.
You know, no, thank you. Yeah, thank you for emphasizing that point. And again, like what Pablo said, like that's the biggest reason like t-distributions are really useful. Like I think you concisely said that in a good way too, where it's like you have a higher proportion of unlikely events just by the fact that you just have not very many things. So if you have like one unlikely event and there's 5 different, you know, members, right? And you have one that's really unlikely, well, that's 20% of your values are these really unlikely events. And so we have to kind of account for that. But if you increase your sample size to like 1,000 different events, well, that one unlikely event is only 1,000th, you know, of your whole sample. So that's kind of like the reasoning on it too. But that's a really important point, I think. Thank you for emphasizing, Pablo. So cool, guys. So I'm going to go ahead and end it here. And I'll go ahead and stop recording.